So hello, I'm Benjamin. So today I'm gonna present a joint work between EDF, so with Goehry and Yadig, and the University Paris Sud with Pascal, Jean-Michel, and me. And so in this work, we present an adaptation for random forests in the context of time series. So the presentation is cut in three parts. The first part, I will just recall what a random forest is, and will point out one issue in the construction when talking about time series. In the second part, I will show the adaptation we propose, and in the last part, the application we did on load forecasting and a conclusion. So we have a training data set, so with n observation, xi, yi, so y can be written of this form, and the goal is to estimate the regression function f based on the n observations, and we do it using random forests. So before explaining what a random forest is, I have to explain what a regression tree is. So a tree is built by a recursive partitioning. So here I put myself, we have two variables, and the goal is to, at each step of this construction, find the best split, minimizing some criterion. So if y is continuous, the criterion is the variance. So if we are in this space here, we look for the best split, so a variable and the location of that variable, such that once you split, you minimize the variance. So this here, it's T2, you cut here, and then you repeat it on the new region, so here, here, and here. And based on this partitioning, you can associate a binary tree which match, where each nodes match how the space was cut. And so you have your tree, and when there's a new observation, you look where the new observation falls, and you associate the prediction will be the constant associated to the region. So this is a tree. Tree have some issues, and Wyman had the idea in 2001 to introduce the random forest to address these problems. So random forest is a big collection of trees, and each tree is computed separately. So in order to explain how a random forest is built, you just have to explain how to construct one tree. So the first step is to draw randomly alpha endpoints, which may equal to n among the endpoints, so with or without replacement. So this is called the bootstrapping step. And then based on these alpha endpoints, you construct the tree. So there's a small difference, so it's not that important. And so random forests are known to perform really well in many applications. They are fast, they are easy to tune, but there's a small issue. And this is concerning the bootstrapping step. So the bootstrap step aims to replicate the distribution of the data set. And so this is adapted to observations which are IID. But when there is some kind of dependence in the data, the dependence will be destroyed. And so here is an example. So on the left side, you have a load of a building over the month of January, and on the right side, you have the bootstrap load. And you know that this doesn't look like this, but this will be used to construct a regression tree. And we think that maybe changing this step and having a new set which looks much more like this one, we will improve the performance of the random forests. So the adaptation we propose is to replace the standard bootstrap with a block bootstrap. So here's an example. So here is the load from the previous slide. And here on the right side, you have a new data set using a block bootstrap. So I will explain how to construct this, but this looks much more like the original load. And so we think that using this one instead of this one, we will improve the performance of the forest. And so the algorithm, the new algorithm is just changing this line here. And so we have a new parameter, which is the block size parameter, which we denote here by ln. But the rest is the same. So to construct block bootstraps, there are many ways. The most common ones are the non-overlapping block bootstrap and the moving block bootstrap. So in the non-overlapping block bootstrap, you have your time series, so with n observations, and you pre-cut in blocks of some size. So here, if I have 9 observations, and the block size is 3, we do blocks of 3. And once this is done, you draw randomly, not among the observations, but among the blocks. So you take the first block, then the second block, and then maybe the first block again, and this will be your new data set. And in this new data set, you are sure that in each block you have the dependent structure preserved. In the moving block bootstrap, it's a bit different. The blocks can be overlapping and are not predetermined, like in the non-overlapping block bootstrap. So the first step to build a block is to draw a random index between 1 and the number of observations. And then once this index is chosen, you take the next consecutive observations. So if the random index is 2 and the block size is 3, you take the block 2, 3, 4, you add it to your new set, and then you repeat it. 3, 4, 5, and so you repeat this until you have enough observations. So we implemented this method in R. So we did it some kind of extension of the package called Ranger. So there are many packages for trees and random forest, but Ranger is pretty easy to manipulate, contrary to random forest, at least for the code part. And so if you are familiar with Ranger, it's the same, we just added 2 main new parameters. So to build one forest, so which is denoted forest TS, you input your equation, your data, and then you have one parameter which determines the variant you want to use, moving, non-overlapping, but there are many others, and the block size, which is constant. And the prediction is the same as in random forests. And so the application we did is on load forecasting. So we took a building called Unilab Patrick, which belongs to a big collection of buildings in the USA. And we have the hourly observations over 1 year. So here on the right bottom side, you have the weekly load profile. And we have also access to the temperature and a schedule. So the schedule is just saying, is it a break day, a normal day, or a holiday? And the goal here is to forecast at the 24-hour horizon, which we denote here by YT. And to predict YT, we use the consumption the day before and the week before, the temperature at time t, so we suppose we know somehow the future for the temperature, the schedule, and some other calendars variables. So the goal of this work was just to show that replacing one single step in the construction of the random forest, we improve the performance in time series. So we just compare to a standard random forest, since it's the goal. So I didn't say it, but we have it. The data is over 1 year. The training is from January to October. We have a validation set over the month of November, and the test is on December. So we We optimized M-try over the validation set. And we have a grid of parameters for the block size, which we also optimize over the validation set. We run this 50 times, and we observe the errors for each variant. So in blue is the IID. So the IID is the standard random forest, so the basic one. And in green, you have the variant. So I didn't talk about the circular, but it's pretty close to the moving, actually. And so for the moving and the non-overlapping, we have an improvement, and we have an improvement up to 10% for the RMSE. And on the right side, we didn't fix the block size, we just fixed the M-try parameter. And we looked at the evolution of the error according to the block size. So the black line here is the standard random forest, which we try to beat. And in blue, red, and green, you have the other variants. So if the block size is too big, the performance is worse. But we still have a big window of parameter where our variants do better and pretty good. And the optimal size seems to be around 24 hours. So I don't know if it's just a coincidence or not, but it corresponds to the horizon forecasting. So I will conclude here. I have a lot of time. We introduced a new way to incorporate the dependence structure in random forest, so just by replacing one step. And doing so, we improved the performance, so at least over the standard random forest. So if you are familiar with random forest, you may know that the variable importance can be defined pretty easily. We redefined it for the block bootstrap procedure, but it's still a work ongoing. And I will leave some references and take any questions if there are any.
Questions, comments, wishes?
Hi. One question: would it not also be possible to, sorry, it's quite really loud, to do some variable transformation to try to create stationary variables and then be able to surpass the whole bootstrapping game?
Sorry, can you repeat?
So maybe in some cases you might have just make a simple transformation, like model the days independently or something like this, the weekdays, and then you don't have to model the whole autocorrelation structure of the data. Does that make sense? Like
can you
trend
repeat
or something like this?
I didn't understand the question.
Okay, maybe I'll ask you afterwards. Otherwise,
I have a related question. So if I understand it correctly, the motivation for block bootstrap-based random forest is the dependence over time, right? Or is that the need for the block-based bootstrap, or is that the motivation, or is it something else that basically motivates the block-based bootstrap?
So the idea of the block bootstrap is motivation is to in a block bootstrap, the idea is that the blocks are kind of independent, but in each block the dependence is preserved, and that's
exactly. But that's why you need the blocks, because if you use the standard bootstrap, that would assume independence among the observations, right? That's why you need. Or do I misunderstand?
Yeah. Yes.
Yeah. So, and I think so. My follow-up question is related to yours, because I think, or maybe that's a naive view, the block bootstrap is, and this is also related to some of the references you had, is motivated to handle stationary time series.
Yes.
And the challenge then, and this also relates to your application, because there you had some components which would usually be considered to be non-stationary, for example, periodicity, into their periodicity. And how does the block bootstrap handle that? Because in a sense, you seem to be applying the block bootstrap on a time series which has both a stationary component and a non-stationary component.
Yeah, so there are seasonal block bootstraps which exist. We did implement it also. I didn't talk about it, but because basically the free variants which are here give enough work already. But you are right, and I can't really explain what you are that theoretically this kind of bootstrap works when the data is stationary.
Okay.
But yeah, I have no answer to
We
this
can talk
question.
more afterwards. More questions, comments, suggestions? Yeah.
So just on that point of the seasonality, because you've got hourly data, your seasonality is going to be of length 24. And so your block, to preserve seasonality, you make block lengths of 24, which is what you ended up finding accidentally, I think, by minimizing the error measure. So I think you ended up with essentially a seasonal block bootstrap, even though you didn't seem to be starting with that objective.
So you're asking if we have some way to find an optimal parameter without, just by looking the data?
I'm just explaining to you that you ended up with a seasonal block bootstrap by accident because you chose a length of 24.
Can you repeat that?
Sorry.
So you ended up with a bootstrap of a block length of 24. Mm-hmm. There's 24 hours in a day. So you ended up with a seasonal block bootstrap.
Yes.
So you dealt with the seasonality through that mechanism.
Yes. That is right, yes.
Wouldn't you then also expect a dip in the error with a multiple of 24? So with 48? Or was it also in the graph?
Well, on the graph there is 48 also, but this is worse. So multiple of the seasonality doesn't necessarily work for the block bootstrap here.